Okay, thank you very much for the intro. And yeah, today we're going to focus on the optimization portion of NC Simul, where we can end up increasing machining profits with the CNC digital twin. And what I'm going to do first is just give you a quick introduction to NC Simul in general, in case you don't know how the day-to-day process normally works with NC Simul. So how you would normally simulate and verify your program before going ahead and doing the optimization that we're going to focus on today. So I'll do all of that really quickly. I won't go through everything. We did do a different webinar a couple weeks ago. If you're interested in seeing that, it focuses on the first 3 steps, and I can get that to you if you need that link or that contact. But we'll do a quick overview, and then we'll jump right into the optimization. So what NC Simul is doing is a true G-code certification, meaning that we're running the true post-process G-code and doing the simulation on that, as well as a virtual part inspection at the very end. And today, there's really no limitation for where that G-code can be coming from. You can manually program it. It can be coming from any of these various CAM systems, and it can be working for any machining type. So 2-axis is Swiss turning, 2.5, all the way to 5, mill-turn, and so on. And this is how we're doing it. We're taking all of these aspects that you've already created inside your CAM system, and we're assembling them into the machine digital twin. So that would be your part, your fixture, your rough stock, your G-code, and the digital twin that we create. And of course, if you don't have any of that available, you can create any of those items inside NC Simul as well. But these are the ones that we have direct links to. So if you have projects created in any of these CAM systems, we have a connector that can pass all of that data through automatically. And the same thing is true for no limitations on what machines we can simulate. So we can both simulate and optimize anything you're seeing here. And basically, at this point, you can just say that we could cover the entire market. So these are the 3 things that we'll be focusing on today. We're going to do 3 different levels of optimization. We're going to have an air cutting one, an adaptive or in material with chip thickness and chip load, and then a machine power optimization where we can use the maximum power of the machine to kind of limit the stress on your spindle. And just as the very last quick overview here, this would be your normal process all the way end to end with NC Simul. The first thing you would do was import the G-code, and NC Simul runs a full verification, and it parses the G-code entirely, meaning that it's going to find any undefined codes, any over travels ahead of time. That's very unique to us, as well as that's a separate step than anything else, meaning it's really fast to verify. It runs at the very beginning really quickly, automatically, and then you don't have to sit there through the simulation to figure out that something is going to go wrong when you load the program at the machine. So that would be your normal first step. The normal second step would be the actual high-end simulation, and that's where all the material removal comes off the part, and you catch anything to do with collisions and motion, so your crashes, cutting without coolant, cutting without the spindle on, clipping the fixturing, that sort of thing. And then at the end of that, you do a visual part inspection where you compare the original part model that you programmed from inside your CAM to what we just cut with the post-process G-code. And then you can see if you're gouging the part anywhere, if you're leaving excess material, or if you're hitting all of your tolerances. And again, we're not going to do all of that today, but the idea is the project that I showed you has been verified for those 3 steps, and then we're going to focus on the optimization. The only other thing to mention here is we do provide automatic documentation for the shop floor, which anytime you change something inside the 3D environment, you can output those new updated sheets if you change a tool length or if you change a setup location or something like that. And the other thing we have is the NC Player, which is completely free and license free. And it's basically a light version of the software that you can then distribute across the shop floor. And that way, if any other machinists want to take a peek at what it's doing at every tool change or watch the simulation, they can do that on the shop floor as well. The only thing they're not allowed to do in that module is edit or add anything else. Those are strictly locked to the programmers, but you can have as many of those seats as you want. So this is what we're actually diving into. here's our optimization. And again, like I was saying, there's 3 levels to it. So the first one was air cutting. Anytime NC Simul detects that you are outside of material, you can increase that current feed rate from whatever it is to either an F max for your machine or all the way into rapid if you wanted to use G0. But that's just going to reduce our part cycle time strictly. And that's a pretty simple calculation. It just knows where the rest stock is at any given point and knows when NC Simul is not touching that, and we can speed it up. The second one I'll show you is the in-material optimization with physics-based parameters, which means either for a chip thickness or a chip flow, depending on if you have a hard or soft material. And you can kind of see in the pictures on the right-hand side here what it's doing. So as it goes through less material, it'll speed up the feed rate. And as it hits more material, it'll slow it down or have a correction if it thinks that you're going to break the tool. And the third one we can do is utilizing the maximum machine power. And this one will eliminate any spindle overload risks, like it says, so that you're not overrunning your spindle. And the cool thing about that one is you don't have to run a proven program ahead of time at the real machine. You can use all the parameters inside the digital twin and all the tool parameters to be able to verify everything completely ahead of time. With the in-material one, you want to make sure that you run it at the machine once and you have a good result. And then based on that, you can kind of up all your other parameters to those maximum levels. That way you're getting your best cutting surfaces and things like that. So we'll do one of each of those today as we move through them. And just a final couple takeaways that we're going to see in the next step. A strong 3-step process we talked about. We won't see that today, but that was the G-code parsing, the simulation, and the verification, which includes verifying all subroutines and macros in their entirety. So anytime something is called in the background, it's going to be automatically incorporated from the archive file that will download from your real machine. And that way you can verify that everything is behaving exactly the same way that your real machine is behaving. So that goes down to anything as little as the way the dog-leg motion is programmed as a 0 or 1 in your real machine. We're going to want to know exactly what that's doing. You have to remember this would be viable for any machine. So just because you're using a 3-axis machine and you normally wouldn't use it for collision verification, you can definitely still run it for the optimization. If you're running a solid number of pieces or parts, you're going to end up gaining a lot of savings over time with that. But then obviously you can work all the way up to your 5-axis or mill turns and be able to do both ends of it, the optimization and the collision detection. We'll see some side-by-side graphing options of, again, the chip thickness, chip load, power of the machine, before and after the optimization. And you can see if there's any spiking that you need to take a look at. And then when you're done with that, NC Simul will automatically rewrite all the feeds for the program. You don't have to do anything except hit generate. And based on the parameters and conditions that it's found, it'll automatically rewrite the G-code for you. And then at the end of that, it's going to automatically compare the G-code that it just wrote to your original one, and it's going to highlight the lines and show you what lines have been modified. And it also creates another simulation process for you automatically as well. So if you wanted to go back in with, I'll show you where it is, but if you wanted to go back in through a new blue folder, simulation process, and just run the optimized code specifically and see how it's looking with any surfacing and things like that in the NC Simul simulation, it creates a process for that automatically too. Okay, so that's what we'll jump into here. Let me just switch over to NC Simul. And this is your main home screen for NC Simul. You have the project that I've already created right here, which you can kind of click on and get a preview of what's inside it if you were looking for a specific machine or a specific simulation process. And as I was saying, I have one created for the normal process and the optimized one already, so we can take a look at those. But if I do want to start it, I just go ahead and double click here and we open it. So again, normally you would want to make sure that everything is running smoothly, everything has been verified, which I've already done, so we can focus on the optimization. but we don't have any collisions in this project, and we can move into the optimization portion. So there's our full machine view. If you did want to see it side by side for any parts of the optimization, you can kind of split the screen and view the material removal on one and the machine on the other, really as many times as you'd like. So the first thing I'll show you and that I want to mention is that we have what's called a cut analysis now as the main base project or base package for NC Simul. And that's this button up here, meaning that we can get all the cutting conditions inside the material without even using the optimization module. The only thing is you can't rewrite the code automatically like I was talking about and we'll go through today, but it's still really nice to be able to come in here and see all the cutting conditions. I won't go through these menus because they'll be the same thing in the optimization, so I'll do those in just a second with you. But basically you set these up to your liking and hit compute, and it does the baseline simulation for you. So these would be our initial cutting conditions or cut analysis. It's broken down into tool sequences, so each tool change, you'll get a sequence in one of these cells, and you can see things in here like your maximum engagement, maximum feed per tooth, volume of material removed, and you can go in and see if anything looks out of whack or really high to begin with. And you can also see the power of the machine that we've kind of limited to looking like it's okay. And you can also see how much time the program's going to run for automatically, how much time of that is inside material versus in rapid, and then we can kind of modify all these things to speed up the program. But again, all of that is still available in the base model, which is new to this version. Okay, the other thing I'll show you here is that we can look at some initial graphs. That way, if you wanted to take a peek at anything to make sure that it wasn't spiking in any areas, you can do that immediately from these first pages. And I can actually click and drag bidirectionally inside here to move both the machine and the G-code. I can jump by tool, I can jump by stop. And actually, if I want to, I can run the simulation with the graph active, and it'll kind of follow along and show you exactly where you're at inside that. So if I start it with the play button up here, you'll see as it starts to progress, this will catch up with both the G-code, the machine, and where you're at based on any of the parameters that you want to see. And there's a lot that you can choose from, especially once we get inside the optimization. So I'll wait to do that, but we'll show you some more inside there. So I'm just going to close the simulation, and now it's time to go into the actual optimization. So that is this icon up here, and it's going to open the optimization module. And you'll see some of the same settings that we were seeing in the initial cut analysis here. But I'll actually go through these now so you can see what we're doing. So the first thing you want to set is a segmentation value. And this is basically how far the tool will move. So I have it set to 10% of the tool diameter before NC Simul decides to recalculate conditions and therefore try to rewrite the feed rates inside the material or in the air cutting. And I have this set usually between 10 and 25%, depending on how precise you want to be. Then you can choose which programs that you want to optimize. So if you're running some macros or subroutines that you didn't want to touch, or you just wanted to run the roughing passes or something like that, where you had these programs broken up, you can check or uncheck any of the ones that you want to allow for optimization. And then once those are checked, it identifies all the tool sequences inside of there. And again, you can check or uncheck any of those sequences that you wanted. So if you only felt like, again, doing a roughing sequence with the same tool and it comes back in later and does a finishing, you could just uncheck that one. And the last thing to set right away is our stock material. And this is what we're going to use to calculate the power of the machine. So you can choose your material type based on the ISO callouts, the designation for that, and then you just put in the empty power of the machine. So this is a pretty powerful spindle we have on this one. So that would be our 1.8 kilowatts of resting machine power. And then all you have to do after that is just hit compute, and it's going to do the same similar thing as the cut analysis. But the good part about this is that we really only have to run the original cut analysis once. So you would open up the optimization module, we run this cut analysis, and then it's ready to go, and then we can start setting optimization parameters after that without having to rerun this initial step. So that should be looking pretty familiar. It's the same thing that we saw originally in the cut analysis. And now we can go in and set our actual optimization parameters. And to do that, we just come in here to our settings tab. And depending on which ones you want to run, I'll do one of each of these. So let's just do the air cutting only to begin with. So I'm going to choose that to optimize. I'm going to leave it on all the sequences that I decided before. So again, it gives you one last chance to decide what you want to optimize. Maybe you just wanted to do air cutting for everything and only in material for the roughing or something like that. That's how you can differentiate those. And then you have some securities. So you can set engagement and retract distances for both untouched and pre-machined materials. That way, as soon as it reaches those distances inside NC-Simul, it reverts you to your original feed rates no matter what. And that way, it gives you a little bit of a cushion if you feel a little bit more comfortable doing it that way. And then at the bottom is where you can set if you want your machine to go into rapid when it's outside of material, or if you want to set a certain cutting feed rate. Same with the tangents. I just left mine both at the initial values. But you could certainly pick up some more time if we were doing those. So I'm just going to hit compute, and it's going to compute strictly for the air cutting. And like I said, it's pretty fast at this point now that we've done all of our initial setup, and I can just keep going back in and picking a different strategy if I want to see any combination of those or a different one entirely. So now if I come down here, we can look at a couple different more tables that we have now. So now we have some optimization results, and you can see how much time that we did save. So instead of 31.5 minutes, just with the air cutting, we've saved 6% or almost 2 minutes on that. And you can also see on the right-hand side, any feed rate that has been modified will be highlighted in purple. So you can definitely verify what's being touched. And you can also do a comparison between the original and the optimized. If you want to see them kind of side by side, you can come in and see where the extra rapids were added. It'll also highlight them in yellow. So if we want to see exactly what's been modified so far, all these yellow areas are where it was far enough outside of material that we threw it into a rapid instead of leaving all that in the feed rate. So we're catching up a lot of time there. And also on any line that you've clicked, you can see the accumulated time up to that point. If I go a little bit farther up and click somewhere, you can see at this point in the program, we used to be at 18.5 minutes, and now we're all the way down to 17.5. So yes, that was our strictly air cutting. And then, like I said, you don't really have to reset the cut analysis every time. I'm just going to go and reset the air cutting and come in here. And now let's add one for adaptive. And when you're in adaptive, you can actually tell it to include air cutting, or you could just have it on its own. But the menus will be the same exact thing that we saw the first time around. So I'm just going to go ahead and compute this one. So we're going to compute the in material for this. So as you can see, it picked up a lot more now that we're touching absolutely everything. You can kind of come down here into your cut info. So that's another way to see it. You can also come in here and look at some different graphs. And now that we're inside the actual optimization, we're going to have a lot more options at what we can see. So we can be putting on the chip thickness, our cutting power, our chip flow, and basically we can switch between any of those that we want to see here. and then I can kind of move through it. And if I see anything that might be spiked or start seeing a concerning point, it's going to be really easy to figure out where that is based on this graph. So that is our chip flow. The cutting power we'll do next, and the chip thickness. So the flow is really the best one to see for this because we were doing a volumetric adaptive strategy. I'm going to reset it one more time. We're going to go back in there, and now let's put on the power of the machine. And this one, inside the strategies, you can kind of see which ones that we're going to optimize. We're going to do it without plunging or ramping. We have our adaptive strategy again, and then you have the power of the machine that you can limit. So we knew that the absolute maximum of this machine was 60 kilowatts. So you can come in here and type whatever you want so that NC-Simul will limit the machine at this. So we put it about 10 under. And then based on that, it's going to figure out the other maximums that it can reach without overrunning that. And if I just come in here and say compute one more time, we'll get one more analysis here, this time for the power. And now let's switch to the cutting power, and then you can come over here and see that it's fairly consistent throughout. We have a little bit of a spike over here, but it's still well under our maximum capability, so we're okay there. And you can do the same thing. So that's our initial, and I could split it here and looked at what it looks like with our optimized one. And then if you want, you can kind of grab them and dock them to wherever you'd like inside the 3D window here if I wanted to see exactly what the difference was when they were side by side. You could do all of that. And they move simultaneously. So again, if you see at the top, you can see the machine moving, the G-code moving, and where you're at inside the simulation or the graphing tab. Okay, so for our final result, I'm just going to turn everything back on. So let's do our air cutting, let's do our adaptive, and let's do the power of the machine. And let's compute it with all of that. And we can head back to our cut info, and let's take a look around. And now that we use the power of the machine to kind of cap it, we're kind of back down to a more reasonable total optimization time. And this program was already pretty well optimized before we even started with it, so I'm not surprised that 5% is about what we're getting. But we can usually expect somewhere in that area some 5, 10, 15% savings if you take into account absolutely everything like that. Yeah, at this point, all that's left to do is to output this code automatically. And all you have to do that is come up here to this generate button. And if you hit that, NC-Simul is automatically going to rewrite all those feed rates where those lines are in purple. And then it's going to open WinDiff automatically, and we can see the difference between what we originally had programmed and the lines that have been changed. Okay. So here it is. And there you go, everything that's highlighted for you automatically. The other thing I was mentioning that it does automatically, if you validate this process here, and I go back to my original project level, you'll see that we have a secondary blue folder that's automatically created. So instead of this original simulation process, we have the optimized process now, which you could then open up and go into and do the simulation, just one last double check time on that. But yeah, that's basically the process here. I'm gonna switch it over now to our Q&A. Let's go back to that. So if anybody has any questions that have come in, feel free again to type them in that chat box. And then, yeah, if you've seen any that come in, I'll be happy to answer it as best as I can.